So we looked at different options, but they're also expensive.
Expensive?
Yeah, you know, me and...
Tunnels are everywhere, most of the time we're unaware, but horses know we're leaking all the time. When looking in the fridge, when coffin does the bidding bridge, you side channels for fun and for the prize, cause side channels are with us all the time.
This foreshadow thing was quite bad.
Yeah.
Yeah, so they dereference some address and it falls, and then the CPU just uses some bits of an invalid page table entry to continue.
That sounds quite broken.
Yeah, I guess building CPUs has just reached a complexity which is super hard to handle.
And super difficult to maintain without introducing bugs.
Yeah, there must be more.
I'm pretty sure there is more. Probably there's some really epic leak somewhere.
Come on, epic leak is a nice microarchitectural attack.
But it's not a side channel.
Okay, so side channel. Let's go back to the definition. In a side channel attack, you obtain metadata and derive data from it. I like that definition.
That's a definition you made up.
Yeah.
And we discussed it already in season 1 and it kind of seems to work.
At least better than some other definitions.
Yeah. And based on that definition, measuring memory access latency, side channel or not?
No, you obtain metadata, but you do not derive anything from it.
But measuring memory access latency and determining whether or not an address was accessed recently, like in flush+reload, that's a side channel.
Yeah. What about meltdown?
Meltdown is not a side channel. Because you get the value directly into a register. Then leaking it maybe, yeah, that's a side channel, but...
Yeah. Spectre? People have called it speculative side channels.
But it's the same as with Meltdown. You get the information directly.
Foreshadow, maybe?
Also the same, you obtain the data directly.
Yeah. So right. So it seems, although this show is called Side Channel Security, in this season, we aren't even talking about side channels. Is that a problem?
But we are. But as Jonas said, we are using side channels to extract the data. You can see the applications of side channels.
Yeah, I agree. And the techniques and methodology used for these attacks are similar.
Yeah.
Also the noise side channels are probabilistic, so same for Spectre, Meltdown and Foreshadow, they all have noise.
Yeah.
And this is what this episode will be about. Noise. I cannot focus like that.
Yeah, me neither.
I need to read this paper and present it to class next week. But with this noise...
Yeah, but what are they doing actually?
I don't know, listening to music or something? Wait. I recognized it. Moonlight. How did it continue?
I don't know.
Moonlight. Ah, moonlight. Makes them shine. Now I remember that.
Okay.
Yeah.
There's so much noise here.
Yeah, I'm trying to read this paper.
No. I'm running Meltdown again. And I get so much noise.
With the patches?
No. This CPU has hardware fixes for Meltdown and Foreshadow.
But noise. Noise is just someone else's data, right?
Exactly. So what am I seeing?
What about the usual strategies? Do you have a dedicated victim program running? You know, that produces some interrupts or that has some cache traffic?
That's a good idea.
Manuel was playing some music and I really didn't understand the lyrics. But then the chorus came up the first time. I remembered the song when it came up the second time and I heard the lyrics again. I had one word. I could remember the next word. And when I heard the next word, the next word. So with every word, I remembered more. Could we build something like that?
You mean like a filter print only the data that is in line with what you're looking for.
But what am I looking for? I'm only leaking data byte-wise.
Well, you could change that.
So you mean like leaking 2 bytes at a time? And check whether the first byte is what I was looking for, and then print the second byte?
Yeah, exactly. Or if you want to reduce noise further, maybe do it with 4, like check 3 and leak 1.
Yes, and with every byte you leak, there is something more you know. I call it the song lyrics attack.
We actually called this the domino attack, as you string together a known value with some new value that you want to learn. And like a string of domino pieces.
Yeah, because the problem of these attacks, same with Riddle and ZombieLoad, is not getting data. You get tons of data.
Yeah.
And also leaking it through the transient domain is easy. 64 bytes in one go.
Yeah, but figuring out what belongs together is more difficult. And now if you want to stitch these things together, you have basically 2 options. Either you filter still in the transient domain and then only leak the parts that match the value that you already have. Or you essentially leak additional data. So basically you string together always 2 bytes and then filter in post-processing.
I like song lyrics attack more, because I think everyone knows this situation. You don't remember the lyrics of a song, but then when you hear words, you remember the next words.
Come back, yeah.
And to get started, you could build a victim program that has a known secret. So you know the prefix, basically. You know what to look for.
Sounds like a plan. Oh, it works.
Really?
Yeah, I can leak the secret.
Wow, this is a new attack.
Maybe.
I just flush and reload in the victim all the time, and that seems to help.
Yeah, but you can leak all of it.
Yeah.
Should we brainstorm what this could be?
Yeah. This is what we had for Meltdown. The CPU takes a morph from the reorder buffer, it schedules it on a load port, an execution unit, basically, that is used for memory loads.
And as this happens, it will allocate an entry in the load buffer.
Yeah.
So the load buffer helps to keep memory loads in order, despite out-of-order execution.
So what is stored in this load buffer?
Well, that's implementation dependent, and usually that's secret because the CPU vendors don't want to talk about these details. But it must be something along the lines of what we have here. Basically, we have the virtual page number to read from. We have the physical page number it has been resolved to, the offset within the page, and the register number where the result should be written to.
The register number.
Yeah, on modern processor you have the named registers like RAX, RBX, RCX, and so on. But they are just kind of like variable names, and internally they are mapped to those dynamically allocated numbered registers on demand.
Fancy. But you can't access these numbered registers or this register file directly, right?
Yeah.
Anyway, the load buffer is accessed, and the store buffer is also accessed to check if there was a recent store that goes to a location that could match this one. Then the L1 is checked because the data might be in L1. Simultaneously, also the LFB is checked, the line fill buffer.
The line fill buffer?
Well, when loading data from memory, or also L2 or L3 to the L1 cache, the L1 cache might be busy right now, or full. Where do you put the data?
And there's an extra storage location just for that.
Yeah. Also for uncacheable memory, because the processor still needs to work with it, needs to put it somewhere temporarily, so it puts it in the line fill buffer.
And then we have access to the TLB, of course.
In Meltdown, yes. In Meltdown, where the user accessible bit is set to 0, there we would fetch this entry from the TLB And then the data is forwarded into the register. Yeah.
Right. And in Foreshadow, there was a page walk because the TLB missed, and then the data was retrieved from L1 and forwarded to the register.
That's right, yeah.
Yeah, and for this vulnerability here, the flushes seem to play a role. So you have a lot of traffic on the L1, actually.
So this could lead to a difficult situation where a load tries to get something from L1, which is being flushed at that very moment.
Mm-hmm. And what happens then? A load normally should succeed within a few cycles, 4 cycles, maybe 5 cycles.
Yeah, but then maybe it cannot. So instead, the CPU will have to do a microcode assist.
A microcode assist?
Yeah, it's like a short sequence of microcode operations to handle more complex situations for instruction execution. And then after the assist, we also add the load operation again. So that load is then successfully performed.
So then we have 2 load operations then, although we only had a single load instruction.
What happens with the first of the 2 loads?
Well, it's stopped, aborted, marks this, do not complete this, something like that.
It's kind of like a zombie thread or process. It's like a load instruction that is there, but also kind of dead.
So you think there's a microcode assist there as well?
A good idea here would be to use performance counters. Performance counters are there for many of these microarchitectural events and properties, and you can use them to disprove a hypothesis. So if you figure out that you suspect it's a microarchitectural assist, but then you don't see any activity on that performance counter, then you can exclude that explanation. But here, yeah, it is microarchitectural assists. The next thing that they suspect is that it leaks from the line fill buffer, which ZombieLoad and Riddle indeed do. And also this, you can confirm this with performance counters. Again, by doing this and seeing the performance counter really increases proportionally.
So let me repeat that. The load is issued. It could be served within 4 cycles by looking up L1 cache and TLB. But then in the L1 cache, a complex load situation occurs because of the parallel flushing and reloading. And that means the load has to be reissued because it wasn't able to retrieve the value within those 4 cycles. Now the old load still can pick up data from the locations it looked up. L1, store buffer, and line fill buffer.
So L1 was Meltdown and Foreshadow, and they patched that in hardware by now, right?
So this could be the store buffer or the line fill buffer.
But you're not changing the value, so it would not be in the store buffer, right?
Mm-hmm, mm-hmm.
Yeah, but I flush and reload it all the time, right? So it would travel through the line fill buffer all the time.
Right, so maybe you leak from the line fill buffer?
But why does that leak? The physical address doesn't even match.
Mm-hmm.
Well, maybe it doesn't, or maybe it does. The load buffer here probably has some field for offset and physical page number.
Yeah.
Maybe it is not updating those fields.
Yes. So it would use whatever older value is stored in here.
And that's why you pick up a lot of different data, right? So you just select the offset, like in contrast to Meltdown and Foreshadow.
And this is some kind of then use after free vulnerability where it uses outdated values.
Maybe. A lot of this is just speculation. We don't have the source code of these processors.
Right, yeah. But it's a plausible explanation. And with this, we also have the different types of meltdown type vulnerabilities covered. We have the original meltdown attack, which was a deferred permission check. We had Foreshadow, which was the invalid use of intermediate values. And then we have ZombieLoad, kind of a use after free vulnerability. These are all vulnerability categories that we know from the software world. And now we have them also in the hardware world. For all these vulnerabilities, also there were concurrent finders. For instance, for Meltdown, multiple teams. Foreshadow, KO Löwen. But for ZombieLoad, it was also the authors of the Riddle paper.
Yeah, and there was also the store buffer thing.
Right, yeah.
So maybe that's something they can investigate next.
I'll write an email to Intel. This is a huge security issue.
Yeah, I will also check out this store buffer thing. If the store buffer thing works and your thing works, we might really become famous.
Wait, how did we have this? We can leak our full name.
Yes.
No.
Hey guys.
Hi.
Hey.
This is my girlfriend, Charlotte.
Hi.
You might know each other.
I think we might have seen each other at uni.
So now I always modify the data. So if I write the data to memory.
Yeah, it will first be placed in the store buffer to order the memory operations. You know, the load and the store buffer, they are often considered the mobbed memory ordering buffer.
So as one element then. Okay. But then I should be able to leak a recent value from the store buffer, shouldn't I?
Yeah, well, actually, there are multiple cases there in this store-to-load forwarding mechanism.
Store-to-load forwarding mechanism, what does it distinguish? What cases?
Well, what is the forwarding based on?
The virtual address?
Yeah, or like just a small part of it. You can just use a very small part of the address and compare that one, because comparing the whole address is very expensive.
It's kind of like a predictor then.
Yeah, exactly. It kind of predicts, should this store be forwarded to this load?
And then there must be 4 different cases. The true positive case, where the store to load forwarding mechanism predicts that the data should be forwarded to a load.
Yeah.
And it is actually correct. The address fully matches. Then there must be a second case where it says it shouldn't be forwarded. And it's also correct because the address doesn't match. So the true negative case. I don't think these 2 cases are very interesting, though.
Those 2 cases are already quite interesting. Imagine you perform a store to a location that you cannot write to. So even though you cannot write to it, the entry may still end up in the store buffer. And you can transiently use it only if you have a DLB entry.
So you still need that physical address tag comparison.
Yeah, and this actually forms a DLB side channel then. You can learn whether a page is physically backed by physical memory or whether it currently has a DLB entry or not. So we wrote a paper about that, don't you remember?
Sure. And then there is case number 3, the false negative case. In this case, the store buffer or store to load forwarding mechanism says this data from the store should not be forwarded to the load, but actually it should because the address matches. And then the load operates on outdated values because they were changed in the meantime.
This is where it gets interesting. This is the Spectre STL case where a load takes outdated data transiently. So kind of a race condition. The operation would have been valid at a different point in time.
And 4th, the false positive case, where the prediction says forward this store to the load based on the partial address match, but the full address does not match.
Wow, if that works, that would give a similar case, a similar leakage scenario as in the previous attacks that we looked at. I do get some data, but what do I attack with it? The store buffer is divided between the hyperthreads. They don't share the entries competitively.
So within the same context, maybe a sandbox?
Then I would have to write that in JavaScript.
That should be doable. In the Fallout paper, we did that with the data pounds attack, which exploits the true positive, true negative case.
Then maybe the operating system.
But what would you attack in the operating system?
Disk encryption?
Yeah, but I think this is getting a bit too much for this episode. I think you should wrap up.
I found a novel attack.
Me too.
On my test system again? Maybe that's why it's crashing all the time.
Not just on your test system, on any system.
One hyperthread leaks data from the fill buffer of the other hyperthread.
And we reported this to Intel already. And I found something with the store buffer.
And I just got a mail.
Let me check.
Thank you for your submission. The vulnerability you described to us, leaking from the fill buffer and other buffers, appears to overlap with the attacks described in the Riddle and ZombieLoad papers.
I also got one. Thank you for your submission. The vulnerability you described seems to overlap with the ones you reported in the Fallout paper.
The server froze again? What are you doing?
Claudio, I think I'm seeing some weird behavior with your test system.
Damn, I have to power cycle that every single time. What are you doing?
I'm just running a simple loop in an enclave.
But why would that freeze my server?